Okay. So, this first problem that I gave you, I'm going to give you a brief introduction into organic chemistry because some of you have seen it, some of you haven't. Some of you study organic chemistry extensively. Personally, I hated organic chemistry, but that's just me. Now, so if you look on this problem, and this is what's weird in terms of how this structure changes. So you've got butane, C4H10 occurs in two isomeric forms. Now, isomers have the same number of carbon atoms. You just change the arrangement of where the molecules are, or where the carbon atoms are located within the molecule. Okay, so you just break a bond and then you reform it. So if you look at this, you have butane, C4H10, and then you have N-butane, and then isobutane 2-methylpropane. So when you look at organic groups, and if you ever study organic, you have to memorize a whole bunch of different stuff. You have basically carbon atoms are somewhat like a Swiss Army knife, and since you can put a whole bunch of different things with them, you could put alcohol groups, which is what you all studied yesterday, where you chuck an OH group on it. You can chuck carboxyl groups on them. You can chuck, in this case, a methyl group. Okay, a methyl group is a carbon with 3 hydrogens around it. Okay, or you could just have a straight chain of carbon. So, and that's the beauty of carbon, is that it bonds with so many different things, and this is why we are basically a carbon-based society. You look at plastics. Okay, hey, we want to make clear plastic. We want to make blue plastic. We want to make red plastic. We want to make plastic that's bendable. We want to make plastic that's hard. Well, so what we figured out how to do is change the arrangement of these carbon atoms and the chains that we hook up to them, and then that determines the properties of the plastics. So, you know, if you want saran wrap, well, that's a completely different structure than if you want to make a bottle of, then you're going to use plastic to make a bottle of water out of, okay? They're completely different, okay? So they both have certain things in common. If you look at saran wrap or you look at that plastic, they're both transparent. Light passes through them without altering the nature of light. Okay, it passes through. It didn't, it'd be black. Okay, because it would absorb all the light. So, Liz, can you do me a favor and go kick that? No, I love my AP physics students, but right now they're being loud. So just kick that door so that door shuts, or kick the can.
Kick it.
Oh, sorry.
Kick it.
Not
Not dramatic.
Thank you. Okay, so let's look at these two structures. Now, here's the beauty to a certain extent of organic chemistry, especially dealing with carbons. If you can count to 4, this is always the old joke, if you can count to 4, you can do organic chemistry with carbons, because carbon atoms have 4 valence electrons, and so you just have to make everything add up to 4 around each carbon atom. So if you look at the name, so you have iso, or you have butane. What does the ane indicate in terms of the bonds? All single bonds, right? So what that means is that each one of these carbons is going to form single bonds.
Is this going to be on the test tomorrow?
Directly? Am I going to make you draw the structure? No.
Any structure?
But I might give you the structure and say, okay, what's going to have the higher boiling point? I'm not going to actually have to draw it. Okay. All right. So if you can count to 4, you can do organic.
I'm here to condemn you for forsaking me from the booth.
There's another piece. There's one last piece in there, right there in the box.
Oh, pizza.
Go ahead and condemn me. Okay. All right. So basically, because these are all hydrogens, okay, you just go around and you chuck a bunch of hydrogens on them, okay? All right. Now, based upon this structure, what hybridization does carbon undergo?
SP.
SP, SP2, or SP3?
SP3.
Why, Wheels?
It has 4 areas of high electron density.
Beautiful. Okay. Count around, you have 4. Now, and there's this handy dandy little deal that says on any straight carbon chain like this, if you take the number of carbons, which is N, to get the number of hydrogens, it's 2N plus 2. So if you look at this, you have 4 carbon atoms. So that's C4. And then if you take 2 times 4, you get 8, add 2 for it. That's how you get the C4H10. So it doesn't, so if this was 3, you'd have, you know, whatever. So that's the simplest way to do this with long straight structures. All right.
Is that only for the?
Only for anes. It doesn't work with enes or ynes.
Okay.
Okay. Only works with this. So here's the deal. So let's say that you're going to have this structure. If it were to run into another molecule, could you have hydrogen bonding?
No.
Why not? There's
Because
a lot of hydrogen.
Doesn't
there's
have
no hydrogen
nitrogen,
bonded
oxygen,
to
or fluorine.
nitrogen, fluorine, or oxygen.
Right, because you have to have this, basically, when you look at this hydrogen electron is going to spend a lot of time here, but it really won't make this end necessarily positive, because carbon is kind of this low maintenance kind of thing. It's kind of chill. It's like, I got 4, yeah, I don't know what to do. I could give away 4, I could take in 4. I don't know, I'm just going to hang out. Okay, it's kind of this like Jamaican mindset, you know, who doesn't know what to do. So it just shares its electrons, okay? You know, not a big deal. So, because of the linear structure of this, do you think the London dispersion forces, and Mr. Flett, love you to death, but don't answer. So,
Right.
if you were to put this beside another one, do you think the London dispersion forces would be relatively strong or relatively weak?
Relatively strong.
Why?
Because it has a large electron cloud, so it uses a temporary dipole.
True, but not what I'm looking for.
It has a lot of surface.
A lot of surface area, it's linear, right? I don't have these big protruding things that are sticking out. So if you put another one right beside it, there is a large electron cloud. But not only that, but the edge of that electron cloud is pretty linear. So it could bond pretty easily to another one, okay, in terms of inducing that dipole moment, okay? All right. So now you got that one. That's the easy one. Now this isobutane 2-methylpropane. So you kind of have to know a little bit of organic. So here's the deal. So if you look on that one, you got 3 carbons, a hydrogen, a hydrogen, a hydrogen, a hydrogen, a hydrogen, a hydrogen, a hydrogen. Now, when you get into this deal with this 2-methyl, what the 2 indicates is the number of the carbon atom that this methyl group is stuck to, okay? Well, and typically what you do, if you were when you get into like these big complex ones, you start counting from the shortest side, and then you work your way either left or right. This one, it really doesn't make any difference which side you start from, because the only carbon that's in the middle is 2, okay? So you've got a methyl group, and again, I'm not going to expect you to have this memorized for the test tomorrow. I'm just showing you how this deal works. So you've got 2-methyl. So that means you come to the second group, and then you're going to chuck a methyl group, and a methyl group is a carbon with 3 hydrogens around it, okay? So that's a methyl group. So this isn't a methyl group if it's part of a chain, but it can be a methyl group if you chuck it onto one in the middle. Now, this is how you can change the structure. You could have 1 methyl. If it's 1 methyl, you put that CH3 group here. If it's 2 methyl, it's here. So, and then if it was 1, it would just be over here, which would be the same thing. So basically, the only variation you can have on this thing would be 1 methyl or 2 methyl. Okay, so you could actually have a third isomer if you had 1 methyl versus 2 methyl. So all the 2 tells you is that when you get to it, you look, go, oh wow, there's the second carbon atom. That's what I'm going to chuck this methyl group on. So here's the difference. So if you compare this one to, I didn't erase that one. Pretend that first one is still up here, okay? Where it was this big linear one. So based upon these two shapes, well, that first one was this big long one with all these hydrogens on it, right? Which one, just based upon shape, should have the higher boiling point? The first structure or the second one?
First one.
Why?
It
Wheels?
takes more energy to break the intermolecular bond since it has a higher London dispersion forces.
Because it is, talk about
Linear-
shape.
Linear.
Because it's linear, okay? You're going to have more surface area that can come in contact with. This
Wait,
has
so
this,
the boiling point is higher for the first one, or?
yeah, so this one, this boiling point here will be higher because of the fact that when they sit there, okay, like this, right, they have a lot of surface area that can come in contact. So if you create a disturbance in this electric field, then it's easy to transfer that disturbance to the other one because they're right beside each other. Whereas with this one, because it has this huge monstrosity sticking out over here, then because that's sticking out, even on this side that's linear, it isn't as long a chain as this is, so you don't have as much surface area that's in contact. So this one, just based upon its shape, should have a lower boiling point. And that it just goes back to what Leo said. Okay, it's a beautiful answer. Your boiling point is reflective of the bonds that hold these particles together. So if you look at from that lab yesterday, so if you were to look at those groups, okay, hey, compare them. All right, they all have, if you look at from yesterday, the three things you worked with yesterday, what do all three of them have in common in terms of forces? What's the one force they always share?
London dispersion.
London dispersion forces, because they all have hydrogen, or excuse me, because they all have electron clouds. Now, if you look at that though, which one doesn't have hydrogen bonding? The acetone. Now, if you ever work in an organic lab, you're going to deal with a lot of acetone. Acetone has a very, very strong odor. Smells horrible. So, if you open up acetone, you can immediately smell it. It's like, whoa, okay, acetone. So here's the deal. Acetone, because of the fact that it doesn't have that strong of bonds, it has what's called a relatively high vapor pressure. So within a bottle of acetone, in that surface up above it, because you have weak bonds that are holding, relatively weak bonds that are holding it together, you get a lot of acetone molecules that are in that area up above it. Then when you open up the cap, whoo, they go fly, they disperse, and you can smell the acetone. For those of you that have ever taken off nail polish, right, you use acetone. Very distinctive odor to get that nail polish off. So basically what happens is the acetone breaks the bonds that hold the nail polish. On an atomic level, the acetone goes in there and breaks apart the bonds that hold either the nail polish together or hold it onto.
Saying good morning before it's too late.
Okay. That's important. Again with the tie-dye.
Yeah, I forgot what you said when I was getting dressed this morning. Yesterday after school.
Yeah.
Yeah.
Okay with that.
It won't
Okay.
happen tomorrow, I promise.
I want to see you tomorrow.
Exactly.
I won't care.
Wait, why? Or you-
He's going on the band trip.
Going.
Okay, so we've got A done, okay? So then we've also talked about B. On the basis of the molecular structure, identify the isomer that has a higher boiling point, and that's going to be that butane, not the 2-butyl, because of the fact that it's more linear. Okay, so we got that one. Home run deal. Now, and so then we get this, suppose a point in butane can turn into isobutane. Now, here's the deal. At 25 degrees Celsius, they're both gases, right? Okay? They're both gases at room temperature. And by the way, in gas laws, because some of you used the wrong temperature on that assignment that I just gave back, if you're dealing with gas laws run off of a different temperature. They run off of 0 degrees Celsius. Everything else runs off of 25 degrees Celsius. So some of you are trying to use PV equals nRT, and you were using a 25 degrees Celsius temperature where it should have been 0 degrees Celsius, okay? And so temperature, standard temperature of gas laws is 273. I don't know why. You'd think they could get their act together and say, hey, everybody, let's go off the same number. No, they haven't. All right,
It's high noon. All right, we're done.
good.
2 more days.
Okay, believe me, I know. All right,
We're gonna carry it on to the end.
so they're both gases. So relatively, do you think the intermolecular forces in N-butane and isobutane are relatively strong or relatively weak? Weak, why?
Because they're a gas.
Yeah, if they were strong, guess what?
They'd be a solid.
Yeah. So, you got butane, right? Okay, here we go. And then you can have isobutane. So write the expression for the equilibrium constant. So we're going to go back to this value of K. So we've talked about K and we've talked about K and we've talked about K. We've talked about KP, we've talked about KC, we've talked about KA, we've talked about KB, we've talked about KSP. So when you talk about KC, what does that C represent?
Concentration.
Concentration. Oh, God, that hurt. Oh. If it was KP, then that would have to be based upon pressure, but we're talking about KC. So, this one's pretty simple.
You missed high noon.
I know. I was trying to make it. Sorry.
Good afternoon. Good afternoon.
Wait, is this one work?
No, we're just going over it.
Oh.
Okay. So, how are you going to do your
I paid
KC?
at lunch and you brought me a personal pan.
What over what?
Products over
Because I can't do
reactive.
it.
Yeah, so it's
Comes
just
at
going to be the
lunchtime alone.
concentration of your isobutane divided by the concentration of your
It's okay.
butane. Right? Okay? So, is anything squared or cubed?
Did you get fried rice?
No, no,
No. Why?
because you don't have a coefficient.
Yeah, there's no coefficients in front of it. Everything's just a one-to-one ratio. Where'd you go?
Doc Greens.
Doc Greens. It's a Dr. Fiesta.
Hola.
Dr. Party.
Okay. So, we got that one. So, calculate the initial. Now, this is what I promise you I'm going to make you do tomorrow.
Which one?
Like something like C and D. I promise you. Okay? It's going to be some version of something like this. Calculate the initial pressure in the container when the N-butane is first introduced. Okay? Before the reaction starts. So, here's what you have to visualize. I'm going to dump the 0.01 mole sample of pure N-butane, and then I'm going to sit back and watch. So initially, what's the concentration of the isobutane? 0, okay, because we haven't reached equilibrium yet. So, how can you calculate the initial pressure when you're first starting off? What can you do?
I'm gonna say nerd.
Herfner, okay? You've got everything. You've got the temperature, you've got the number of moles, you've got the volume, and you've got everything else. So all the thing you have to do is plug and chug numbers into the equation. That's all you have to do. Just choose wisely in terms of your gas law constant. Yes?
Do you want us to use 0.08206 or 821 for the gas line?
I just always use 0.0821. This has, all of these numbers have like only 2 significant digits. So even if you use the 0.08206, it really won't gain you anything because you got to round it to 2 or 3 significant digits anyway. So I just go with the 0.0821.
I have a question. You just said something, I didn't really understand what you were meaning about it being 0 degrees Celsius, but this says 25, so would we?
But this just means it isn't under standard conditions in terms of gas laws.
Okay.
In standard conditions on gas laws, the temperature would be 0. Okay?
That's Kelvin.
Yeah.
Not Kelvin. Yes, ma'am.
273 Kelvin.
Am I testing? Like right now?
Because we had, I just want to make sure we're not bothering you.
No, I'm just lecturing. You're good.
Thank you.
Thank you. Okay. So, only time, and here's why this works. If you look at PV equals nRT and standard conditions of a gas law, okay, of a gas law, you have 1 mole of gas, you have 0.0821, you have 273 Kelvin, right? And then if you divide that by a pressure of 1 atmosphere, so basically somebody take 0.0821 and multiply that by 273.
22.41.
You get 22.4, okay?
Can that be a
That's the
constant?
wrong thing. Wait, never mind.
How'd you get 1?
Okay.
He's not doing
No, no,
this.
no, I'm not doing this problem. I'm doing something else. Okay? What I'm showing you is that under standard conditions, 1 mole of any gas under standard conditions of gas laws occupies 22.4 liters.
I never thought of it that way. That's so cool.
What do you think, he just randomly made up the number?
Yeah.
22.4, that sounds cool.
He just like woke up one day. It was kind of like Back to the Future, where he was like
Yes.
about the time machine. You know, he was just like
Exactly like that.
0.0821 later that atmosphere volt.
Okay, here, let me ask you all this question, and I want a serious answer. Okay? You all are done with AP Chemistry, you've been through Chem 1, Chem 2, and now AP Chemistry. Why is Avogadro's number 6.02 times 10 to the 23rd?
Because that's what
That's
our
how
chemistry
many-
teacher told us.
That's how many
Didn't we
atoms
already
and
talk about
molecules are
this?
in a mole.
Why? But why isn't it 10? Why isn't it 50? Why
Because they're
6.02
small,
times
so it
10
has
to
to
the
be a
23rd?
big number.
Ratio.
Of what?
I don't know. That's what they picked. I don't know how we figured it out. He was smart. I'm not
We
that
talked
smart.
about this, but I don't remember what you said.
He did his thing. I'm not there
He
yet.
did his thing.
I don't know. I'm not that smart yet.
It's particles per mole.
Okay, Avogadro, first off, never even found the number
Then why is it his number?
because he proposed the hypothesis that a mole of any gas will contain the same number of particles.
Let's make
Well,
it Emma's number.
So in 1811, he proposed the hypothesis, but they didn't have the technology to count the numbers.
I
They'd
feel
actually
like
get the numbers.
the person who
So,
figured out the number.
Here's the big picture. Okay, so if nothing else, I at least want you all to understand this. Let's say that you have a mole of carbon. How many grams of carbon would you have?
12.01.
Why 12?
Because that's what it
Because
says.
that's
on
how
the
much it
paper.
weighs. Because if you do dirt
No,
over P,
no,
that's
no.
what you get.
No, no, no.
Because we can all read numbers.
But
Dirt.
you don't know what the numbers mean.
I know that it means the molar mass of carbon.
Okay, but why 12 grams?
Because that's
Why
how
not
many
10?
grams are in a mole of carbon.
Like, that's
That's
just
how
what
many
it is.
grams
Like, it's
are in
determined. It's
6
not
point-
gonna
No,
change.
no, no, no,
Whatever.
no. Okay, then you find a mole, you have to look at the sequence. In terms of what they figured out first, they figured out first the relative atomic mass of the values.
Where'd they get that from?
Basically, it was a comparison of equal volumes. So, like, literally, this is what I did with my Chem 1 students. They had 2 cups.
Okay, you
On a
and your
balance
Chem
beam.
1 students actually learn. We didn't do that.
Well, I'm telling you. So, when we had
learned
small
stuff.
Can we do
marshmallows,
it?
It was a lot easier.
I'm out of marshmallows, or I would.
You guys, they got marshmallows?
No. Yeah, they got
Wow.
Why don't we get marshmallows? Where are my
Don't
marshmallows?
get all up like this, okay? So, they had small marshmallows and they had medium-sized marshmallows and they had the big honking large marshmallows.
I don't
And
think
so, we defined the small
hydrogen.
marshmallow to have a value of 1 atomic mass unit, okay? So, then they put a medium over here and then they count how
don't actually
many
have to know
small ones it took to balance out a medium. And that was like 13.
They did that with hydrogen.
Yes. So
How'd they
basically,
do that? though? Like, how?
what do you mean?
Miss Shirts didn't teach us this.
Yeah.
Well,
I just know
this
what
is this
makes
whole
up
lab that I wrote for my Chem 1, and it was cool. So that was just a visual way of saying, wow, it takes
You did a
13.
lab without the chemicals.
We did 13.
Did you make them wear goggles
I did actually.
to play with marshmallows?
Dangerous marshmallow.
They could explode.
You never know. Hey, they were Chem 1 students. Come on.
They have a higher
It's a habit.
So,
I'm gonna
here's
put a
the point.
marshmallow in
So they
mine.
said, oh, that's 13. So we defined the relative mass of the medium-sized marshmallows to have a value of 13. The smallest were 1. This had a value of 13. So that's basically what they did. They said, okay, technically it's 1 atomic mass unit is defined as 1/12 of a carbon atom, which makes it hydrogen. So it's basically the same thing. So if you basically what they did, they had the relative atomic mass values first. But they said, look, we're never going to work with individual atoms. but the metric system was all the rage. So they said, okay, we're just going to take carbon, which has a relative atomic mass of 12 atomic mass units, and we're going to scratch out atomic mass units, and we're just going to put grams on the end of it. So all they did is they took all of the relative atomic masses that they had, marked out atomic mass unit, and said, okay, we're going to define this as being whatever that value is in grams. Magnesium, 24.3 grams. Neon, whatever that is. But then the challenge became, how many atoms does it take to equal 12 grams? So if you have a balance, okay? And again, this is what I had my kids do, okay? They had cups, right? So over here, they put the equivalent of 12 grams. Let's say it's carbon atoms. So then you come in here, and you're going to start chucking carbon atoms and carbon atoms and carbon atoms into this cup over here until it balances out. And what it turns out is that it takes 6.02 times 10 to the 23rd carbon atoms to equal 12 grams, to equal the relative atomic mass measured in grams. Because if you only put 1,000 over here, if you only put 1,000 carbon atoms over here, would it balance?
How'd they count out that?
That's what I'm trying to
You've
think.
always told us you can't just pluck out one atom.
No,
Like,
you can't.
just say.
But the whole key, this is why
How
Avogadro
does
just
this
proposed the
help
hypothesis, okay?
This
The
is
easy,
not
what
But
they
they proved
actually did was they used Faraday's constant, if you remember Faraday's constant, which is the charge on a mole of electrons. And this came after a guy by the name of Michael Millikan did what's known as the oil drop experiment, and
I
he
wish it
found
was
the
called
the
Millikan's
mass to
constant
charge
instead.
ratio on an oil drop. So that's a whole story. But basically, he dropped the oil, ran it through an electric field, and got to the point where the oil drop would hover. So he had a gravitational force acting down and an electrical force acting up. So he found the charge on the oil drop. So then, basically from then, it was just extrapolating that value onto a mole. And so once they found the charge, because charge is a relatively easy value to measure, you can measure voltage, okay, like if you, that's the simplest way. And so they could measure the voltage, and they said, wow, this is the amount of charge on a mole of electrons. Then they took that, from there, worked out Avogadro's number. So this is why Avogadro couldn't actually come up with the number. He just proposed it and said, well, this is what should happen. It's like the first time they discovered helium. Anybody know why helium has the name that it has?
Helios.
First place was on the sun, Helios. Okay, they didn't know it existed, but they looked at the atomic spectrum of the sun, and they saw a spectrum that they had never seen before when they were analyzing light from the sun. Wow, there must be a different element up there. And then they found helium here. Anybody know where actually? Well, now one of the world's largest deposits of helium gas is located?
My bad.
Southwest Kansas. Okay? Southwest Kansas. It was actually a national secret during World War II because they needed the helium for balloons, and so they actually kept that location separate, or secret, I should say. So anyway, so the reason why Avogadro's number is 6.02 times 10 to the 23rd is because it takes that number of atoms combined to equal the relative atomic mass measured in grams. Now, in physics, we use kilomoles, okay? So instead of 12 grams, we work in 12 kilograms. So Avogadro's number in physics is
6.02
times 10 to the 26.
Oh, I got it right.
Okay? Because instead of 12 grams, it's 12 kilograms. If we had chosen pounds, okay, and said, okay, well, we're gonna make a mole be 12 pounds. Okay, Avogadro's number would have been completely different. So there isn't anything magic about Avogadro's number. You just have to view it from the sequence on how it worked. Okay?
Pounds are stupid.
Huh?
Pounds are stupid.
Well, earlier you made it
Tell me
seem
how
like,
bad I am.
you said that the metric system was all the rage. You made it seem like it was a fad.
Well, no, in the sense that they were just really developing the metric system as a unifying system of measurement within the scientific community. We just never bought into it. So, okay.
It's just a stupid theory.
Yeah.
Zeros.
Yeah, there you go. So anyway, so if you do the math on D, you should get like 0.24 atmospheres.
Yeah.
Yeah. Yeah.
Yeah.
Okay. Now, let's talk about E. The N-butane will relax until equilibrium has been established at 25 degrees Celsius. Calculate the total pressure in the container at equilibrium. Justify your answer. What's going to be the pressure?
2.4.
What'd you get?
0.24.
0.24?
Yeah.
Why?
Because no matter what, the same number of moles is going to be in it since it's a 1-to-1 ratio.
Beautiful. Okay.
Yeah.
So your answer to 2E, or yeah, excuse me, to CE part 1 is the same. It's a 1-to-1 ratio. Okay. It is a 1-to-1 ratio. Are you gonna lose some N-butane and make some isobutane? Yeah. But it's still going to be the same number of particles within the system. Okay. There you go. Now, 2 requires some thought, though. Okay? 2 requires some thought. So, if you look at, like, here's N-butane,
Are they the same like chemical
and here's
formula, or
iso.
Are they different?
So you got N
Same
but,
chemical
iso
formula,
but.
different
So,
setup.
Yeah.
what's the initial concentration of your N-butane?
No clue.
0.01. What's this initial concentration?
0.
0. So then what are you going to do?
X
Minus or plus?
minus.
And then over here you're going to put
Plus X.
plus X.
Okay, I have the right number.
Now with this one, because it's in a 1-to-1 ratio, and that, if you look at that Ka or that Kc value, it's 2.5. Now let's talk about that Kc value of only being 2.5. First off, is the forward reaction going to be favored?
Yeah, just a little.
Yes, just a little. Okay? It isn't like that's 2.5 times 10 to the 94th. Okay? For a K value. All right?
Where's the picture?
So, not yet.
I
Still
saw
thinking
that.
about it.
Maybe
We need to choose a spot to put it.
that was more like in physics because you get like, what's the mass of your phone, and it's like,
Mass of the moon.
yeah,
Yeah.
like oh.
Yeah. So it's going to be favored. Now, and here's the other thing that you have to look at: a relative value of K. Since K is just barely above 1, that what that means is this reaction won't go all the way to completion. Okay? It's a relatively small, big K value, if that makes sense. Now, if it had been like 2.5 times 10 to the 94th, something huge, there wouldn't have been any, basically none, 0, zip, butane left. It would all have existed as the iso. So we're going to favor the forward reaction some, but when we establish this equilibrium, we're not going to be too far out of kilter on this deal. So how can we figure out what these X values are?
Put it into the
KC.
equation.
Well, I know Kc is going to equal
Products over
X over
0.010 minus X.